putting in our dilution refrigerator at 10 millikelvin or 4 Kelvin, and we're finding out which ones work. And that made no sense to me. So that's kind of when the idea came that I should actually start a company designing components to actually work properly in the quantum computers. Every component is its own part number with its own price. And so there's nothing, this is what you get. You're not going to get anything else. If you want a different spec, you're not going to get it. Then if you want a different spec, that's a different part number. Everything is its own part number. So by doing that, we can let the customers just go and review all of the technical data, and it's just click by, click by, click by.
Welcome to Manufacturing Insiders. Today I have Andy Cobin with me today. He is a fascinating individual in a fascinating field. Quantum computing is something we hear thrown around a lot. He has some insider information about how quantum computers are made, and he manufactures some of the coolest components I've ever seen. I mean, we're talking like gold-plated superconductors. So Andy, welcome to the podcast today. Can't wait to learn more about what you know.
Sure. Well, thanks for having me. I appreciate it.
So if you could just give us a little bit of a background, you started off getting a degree as a microwave engineer, and you've been working in this field for really almost as long as I've been alive. But tell me a little bit about your story.
Yeah, so I went to Wentworth back in the 80s, and I graduated in 1985. And then I worked for a company called Microwave Associates, which we made microwave components. So I was kind of a design engineer and a product engineer, and I moved on from there to other companies. I even had a microwave company years ago where we were a microwave assembly company. And then in 2016, I decided to start Quantum Microwave, building cryogenic microwave components for superconducting quantum computers.
Wow. So I would have to assume that you know quite a bit about how quantum computers work, given that you're making components for them.
Yeah, so that's not really the case. So it kind of goes back to 2016. I visited a company, IBM, and then I visited a company, Google, and John Hopkins, APL. And they all said the same thing to me. They said, Andy, we are PhDs, researchers, scientists, and we're making these superconducting quantum computers, but nobody makes the proper microwave components for quantum computers. So we're buying everyone's components, and we're putting in our dilution refrigerator at 10 millikelvin or 4 Kelvin, and we're finding out which ones work. And that made no sense to me. So that's kind of when the idea came that I should actually start a company designing components to actually work properly in the quantum computer. So I'm not like a quantum computer expert, but I'm more an expert in the cryogenic components that are needed in the quantum computers. Does that make sense?
It does. It does. So when we talk about like the fundamental unit of quantum computing, it would be the qubit, right?
The qubit, yes.
So to me, it's really kind of mind blowing to try to wrap my head around this. So like I understand the double slit experiment where they proved that a electron or a photon could act like a wave or a particle. And so that's kind of the fundamental concept here, is that there's this duality of the qubit where it can act, it can be either a 1, a 0, or both of them simultaneously or something to that effect.
Yeah, exactly. So a qubit can operate in multi-states where conventional computers are kind of binary. It's a one or a zero. They can be a one and a one or a one and a zero. And so, yeah, all the researchers are trying to come up with the most powerful quantum computer and the best quantum computer. And my job on the hardware side is to protect that qubit. So that's what I'm doing. I'm making components that amplify the qubit. I'm making components that split the qubit. I'm sending qubits in certain directions. I'm filtering the qubit. I'm protecting the qubit from IR reflecting back and damaging the qubit. So we're making the components that make the qubit get to the outside world and still operate properly. That's the goal of what we're doing.
Interesting. So is there actually, like, you're actually manipulating photons? I mean, is that
Well, the qubit is in a microwave frequency, so
okay?
the qubit is generated by a Google or an IBM or an Amazon or any of these quantum computing companies. They make something called a quantum processor, and the quantum processor can be 10 qubits, 100 qubits, 200 qubits, thousands of qubits, and eventually they want to get to millions of qubits. And every qubit is its own individual frequency. And so what we do is the qubit signal is very low. So it's not possible to get that signal out to the outside world. So the first thing we would do is we would amplify the qubit. And so we'd make the signal better. And then we would isolate the qubit. So there's components called isolators and circulators and amplifiers and filters. And what we do is we make components that start at the room temperature world and decrease the power. And you decrease the power, so you're decreasing the heat. So you're going from room temperature down to, all the way down to millikelvins in multiple stages. So we have to keep reducing the power and reducing the power until we get to this 10 millikelvin where the quantum processor is operating. Then we have to use components that amplify the signal in a superconducting mode. So the idea is we want to amplify the signal, but we don't want to use any DC power, which generates heat. So we do things like that. And that's called a superconducting amplifier. So we sell a traveling wave parametric amplifier, and we sell a Josephson junction parametric amplifier. Then we get down to the millikelvins, and we're controlling the qubit. And now we have to bring the qubit back up to the room temperature world. So we come down to the qubits, and then we have to bring it back up to the room temperature world.
Right.
So we make those types of components.
And it's been a little while since I had my last physics class, but kelvins, the number 273 stands out in my mind. What is a millikelvin? Like, how would that translate into?
I think 10 millikelvin is 10 thousandths of a degree above absolute zero.
Okay.
So I don't remember what frequency it is. I mean, what temperature it is, but it's minus 400 and something, 470 degrees Fahrenheit or something like that. It's very, very cold.
Okay. Yeah. So 0 kelvins is negative 273.
Right.
Yep.
Centigrade. Right.
Gotcha. Okay. Or negative 459 Fahrenheit. So we're talking some very, very, very cold temperatures.
Cold temperatures, right.
Wow. What are they using to achieve that type of cold?
I think they do it with helium.
Okay. Yeah, that makes sense. Gotcha.
Right.
So, so this business quantum microwave that you have now, it kind of started off with you reselling somebody else's product, and then you decided that you were going to get into the actual manufacturing process, right?
Right. So we started off, and we still do. We sell for a company called Low Noise Factory, which is out of Gothenburg, Sweden. And Low Noise Factory makes an LNA, which is an indium phosphide hemp. So that particular material, as you go colder in temperature, the noise keeps dropping. The noise figure or the noise temperature keeps dropping. Because when you amplify the qubit, you have to amplify the qubit with no noise or as little noise as possible. So this company makes the best cryogenic low noise amplifier in the industry. So everybody needs that amplifier. So they're in Sweden, and they asked if I would open a company here in the US to distribute their products. So that's what we were doing. And as I'm distributing the products, I asked the owner of Low Noise Factory, I said, would you mind if we develop complementary products to your product? And so if he's making the amplifier, someone needs to make an isolator, and someone needs to make a circulator, someone needs to make filters, someone needs to make couplers, and all of the different components that go around it. So that's what we started to do, and we kept adding them to our marketplace. And then other companies came to us and they said, well, you sell our product. So we're now probably about 5 or 6 companies that we distribute and the products that we make. So when you go onto our marketplace, you can almost buy every cryogenic microwave component that the Amazons, the Googles, the IBMs, the research facilities, and they don't have to wait 6 months for a product. They go on our website, they place an order, the product shipped that day. So we're a in stock online marketplace for state of the art cryogenic components. Yeah.
Wow.
Right.
So did you bring you said that you were going to have some samples for us. Did you bring anything out, or should I pull up your website?
Yeah, pull up my website. I got tied up and I didn't get that done. Sorry about that.
No problem. Yeah, I wanted to show off some of this stuff. Yeah, because I just thought it was so cool, like gold-plated components.
And they're not just gold-plated components. It's the material under the gold plating. Like go under where it says cryogenic components. Is probably the best one because we make other products too. And then scroll. Can you scroll so you can see the components?
Oh, okay. So hang on one second. I'll click on.
Right.
Yeah, get the whole category.
Yeah, keep going. Keep going. So yeah, so the first one, these are like where it says GQE. That's a company we sell for, Gateway Quantum, and those
Okay.
are very low frequency filter, 25 line filters. And the material will be made out of like a OFHC copper, which has very good thermal conductivity. And then it'll be plated with gold, but it won't have any nickel under it. So we make these filters that they're good thermally, they have good RF performance, and they're non-magnetic. So that's magnetic fields also hurt the qubit. If you scroll down a little bit further, you'll see that the copper one, that's an OFHC copper cavity. So people can, that's just for experiments. So a researcher could put their filter in there. They could put their superconducting circuit in there.
Yep.
Yeah, so that's just a test fixture. Yeah, and then if you go look at a few more of them, these ones that say the cryo BRD.
Yep.
Those are kind of like you could put a quantum processor in there, or you could put qubits in there, or you could put amplifiers, whatever your research is, you can put these superconductor components in there, and they're completely shielded from the outside world. So they're thermally excellent. They stop any magnetic fields from going through.
How big is this item physically?
Oh, so they range. Some could be this big and some could be this big. So if you look at the bottom of a superconducting computer, you'll see all of these things like this hanging, and that's where all of the magic is happening, where all of the physicists are developing all of their superconducting circuits. So this is, we call it a breadboard. So like, say an engineer were to make that, they would probably spend a year making the bracket, and then they have to get a mu metal shield made, then they have to get a superconducting shield made, and a copper shield. So we just make it in all different sizes, so the customer can just go click buy, and they can be doing their experiments the next day. Can you scroll down some more? So these ones here that you're looking at are new filters that we're putting in. So we're doing high pass filters. And what a high pass filter means is it passes the frequencies that are above the frequency. A low pass filter passes the filters that are below, and a band pass filter passes to a certain band. So different places in the quantum computer need different types of filtering. So we've created a whole family of filters. So if they want a low pass filter to protect anything of higher frequency, a high pass filter to protect anything on the lower side, and a band pass for any frequencies on the high side and the low side. If you keep scrolling down some more, keep going. Okay, you can see something that says a cryocoupler.
Yep.
So that's if a customer, say they want to send most of the signal straight through the line, but maybe they want just a little bit of a signal coming out for some reason, maybe for a sampling or maybe to do something else. So we make a cryogenic coupler. If you keep scrolling down, you'll see a bias T. So a bias T connects, you have your DC and your RF. The bias T adds the DC and the RF together. So that's what they call a bias T. If you see the thing that says the QIBO, those are actually qubits. It was right.
I see. Yep.
Yeah, so that's actually qubits. So those are superconducting qubits. So people put that in their system so they can characterize their qubit versus our state-of-the-art qubits. Yeah. If you scroll down here, the one that says silent waves, those are traveling wave parametric amplifiers. So as we said, the qubit comes out, the quantum processor brings out all the qubits, but we need to amplify the signal. This is the superconducting amplifier that's used to amplify the qubits.
Wow.
Yeah. And if you look right next to it, you see something called the attenuator.
Yep.
So those attenuators are used to drop the power. So the power is very high at room temperature. And to get colder, you need to drop the power. So they use attenuators in each stage to drop the power. So when they get down to 10 millikelvin, they want to have almost no power because power equals heat. And if you're heating up the plate, you can't achieve the 10 millikelvin temperatures. So, right. So that kind of gives you an idea. We make pretty much every component, from the amplifier to the filter to the attenuator to the coupler. Hold on a second.
Yep.
Sorry about that. That was my dog that just came in. Uh, um, yeah, so we're kind of, I don't want to say the Amazon of cryogenic microwave components, but we're something like that. We're a marketplace where all of the researchers can come and do their experiments. And the goal is the quicker we can get the experiments done, the quicker we can win the race to commercializing the quantum computer.
So where is the quantum computer as a whole right now?
um,
I mean, are there functioning quantum computers that are solving problems, or are we still up against some issues we haven't solved yet?
yeah, so now that's not my expertise, but I would say we still have quite a few years to go. If you talk to experts, some might say 5 years, some may say 10 years. And so to get a good usable quantum computer, we need lots of qubits. And right now we're kind of on the superconducting side. Right now, and I don't know exactly what people are at. They're in the hundreds of qubits, and we need to get to the thousands of qubits, and we need to get to the millions of qubits, and we need higher quality factor qubits, and we need longer coherence time qubits. So there's the big talk about all the software people are doing error correction, and we need really good error correction to get the quantum computers to that usable space where they're really going to solve real world problems. So I don't think we're quite there yet, but I think they're definitely progressing.
Hmm. So when you kind of look at your own sales, I think you said to me before that when it comes to that super cooled portion of the quantum computer, you're kind of the go-to resource. So when you kind of look at your own sales, how have you seen it progress, let's just say over the last 5 years?
Yeah, so we've been growing a lot every year. So if an IBM, and I'm not IBM, so I can't speak for what their goals are, but if their goals are to double the qubits every year, or Google double the qubits every year, Microsoft double the qubits every year, that means these systems are getting bigger, and they have double the components in them, or close to double. And so every year the component growth is just it's just huge. So we keep growing every year, but you can't just keep growing computers so they're the size of a building or something, and they take a power plant to operate. So
Right.
as qubits are as quantum computers are growing in qubits, we have to start learning how to make components smaller. So we're kind of at that infancy stage. When the first computers were made, they took up the size of a building, and
Right.
now they're the size of your cell phone. So we're
Yeah.
kind of in that phase now where all of the components are, a certain size, and they're all connected by cables, and somebody's going one day is going to invent, a circuit that can do the whole thing, or
Yeah. A quantum watch, right?
yeah. So there's a long way to go there, and who knows if it will ever get there. But so we have to make these components that we're making really good. We have to make them even better. We
Mm-hmm.
have to make them smaller, and we have to make them less expensive, because nobody can afford to buy a quantum computer right now. It would cost millions of dollars. So
Sure.
yeah, there's a long ways to go.
Yeah, when one bread, what was it called, a bread basket or a
Our breadboard.
breadboard? Yeah, like one of those costs $6,000. You you need multiple on your computer, and
Well, that breadboard is just a fixture. It's $6,000 without anything on the inside. Then they have to put their much more expensive component inside that. Yeah.
gotcha. Wow.
So yeah. So and that's what we're doing is we're we're taking the same components we have now and we're trying to make them so they're surface mount or so they're hybrid so that they can be built in these tiny little circuits. And it's all doable, and it's all going to happen. So
Yeah, I can imagine it would be there'd be an interesting set of challenges when you're essentially manufacturing components for a largely theoretical and experimental space. When you're a space that's established, like we talked about valves earlier, you gotta, turn off the flow of gas at a certain pressure. You know exactly what you're trying to do. Whereas like with you, it's almost like you have to kind of anticipate what they might be trying to experiment with and build around that.
what you need is you need the professors of these quantum computers, the researchers, to work with the microwave engineers to tell us what they need. So if we get a professor that will say, Andy, this is great, but this is really what I need. And so that's kind of how we go in that direction. And it's interesting because in Europe, and so we sell for a lot of European companies, the professors that develop like an incredible technology in Europe, they're allowed to take that technology and leave the university and start up their own company. So that's why we have a lot of these, state of the art components from Europe, where in the United States, maybe an MIT or a Caltech or someone develops something that's incredible that can change the world. They can't take it out of the university. It belongs to the university.
Oh, that's problematic.
Yeah, so at least that's the way I understand it to be. So we'll get someone from Sweden or Switzerland, and they'll say, "We've developed this. Will you market it for us?" And we say yes, and we work a deal, and we stock them here in the U.S., and they're available to all of these U.S. companies.
Wow. What's the most surprising thing about quantum computing that you think most people don't understand?
The most surprising thing about quantum, I mean, I really don't know. I don't know those answers, to be honest with you. We're down in the nitty gritty, just making very, very simple components in a way that they work cryogenically. Yeah. So, yeah. I mean, according to the experts, it's going to change the world, so,
Yeah.
but I don't know.
How do you test the efficacy of the components that you're building? Like when you say, it's splitting off the high frequency from the low, like I would imagine there's got to be some pretty complex testing procedures.
Yeah, so you need to buy a dilution refrigerator, and those can range anywhere from $10,000 to $500,000, and it's not something that we can afford. So what we do is we're located in Massachusetts, and Massachusetts has something called the Core Technology Program out of UMass in Massachusetts, and they offer Massachusetts residents the opportunity to use their systems. So we take our components to UMass, and they have very sophisticated components, and they test them for us at 10 millikelvin and at 4 Kelvin, and they give us the data. We have the same equipment to test it at room temperature. And so then we put the cryogenic test information on our data sheets. And then we just do a room temperature test kind of in volume. Otherwise, like a dilution refrigerator to get to 10 millikelvin takes 2 days to reach the temperature.
Oh, wow.
Yep. And then you spend a day testing. and it takes another 2 days to get back to room temperature. So every test you do takes a minimum of 5 days.
Holy.
So, so if we did that on every component, we would never be able to make money, or the product would be so expensive. So we give them a lot of 10 pieces, and we let them run it at 10 millikelvin. They give us the data. We post it on our website, and then the researchers are able to say, okay, I can see the components from quantum microwave. They're going to work at 10 millikelvin.
Mm-hmm.
So yeah, that's how we do it.
Wow. Yeah, that's fascinating. And I was just trying to think of like the process of kind of scaling, if these if they kind of work out all the bugs and there's just quantum computers going up all over the place, the manufacturing operation you would need to, have a testing facility and um, a lot of bars of gold to melt down.
Right, right. And some components that are not superconducting, you can test at not as cold temperatures like 4 Kelvin. And those can get down to temperature in an hour or two. But the
Yeah.
ones that go into the superconducting, those are the ones that need to go down to the millikelvin temperatures. And yeah, it's a very expensive testing procedure for sure.
Yeah. What have you learned about the e-commerce process? I mean, you started a website and started selling these. Like, what's some advice that you might have for somebody that has their own kind of e-commerce store where they might be selling some of their custom manufactured components?
Um, yeah, I don't know. So we came up with this idea of every component is its own part number with its own price. And so there's nothing, this is what you get.
Mm-hmm.
You're not going to get anything else. If you want a different spec, you're not going to get it. Then if you want a different spec, that's a different part number.
Right.
Everything is its own part number. So by doing that, we can let the customers just go and review all of the technical data, and it's just click by, click by, click by. So every day, and it's great. It, they click, they buy, we ship it that day or the next day. The money comes into our bank the day afterwards. It's just phenomenal. It saves all of the time of preparing quotes, and
Yeah.
then the customer has to take the quote to purchasing, and all these people have to sign it off, and you eventually get the PO and just click by.
Yeah.
It works great.
Yeah, and you found a hell of a niche. I mean, well, you didn't find it. I mean, there's very few people that would have the expertise to do what you're doing. But I mean, that's such a great place to be where you really don't have a lot of competition in the space. And if somebody needs something to operate in this area of the quantum computer, I mean, this is where you're going to get it.
Right. We're very niche, just in that small little cryogenic section of the quantum computer.
Yep. Yep.
Very niche.
Well, pretty fascinating what you're doing. Looks like you built a pretty awesome business. I wish all the success to you in the future. And certainly, if you need any help on the marketing side, you know where to find it.
Thank you. Appreciate that. Well, it's good to talk to you.
Absolutely, Andy. Anything we missed that you wanted to share?
No, I could just say we are quantum microwave, but we also focus on millimeter wave. So if somebody's making a satellite, we would make the links up in the 30 gigahertz, 40 gigahertz, 60 gigahertz, 100 gigahertz. So that's our other little niche, is we focus on millimeter wave. So, but
Gotcha. Okay.
yeah.
Communications.
Yeah. So we get a lot of, commercial LEO space jobs, and super high power amplifiers, and radio astronomy actually works cryogenically as well. That's how they look at the, what's going on up in the space. So yeah.
So are some of these components things that would be involved? Like if you got a rover up on Mars or something, and you need to obviously send a pretty high power a high frequency transmission to get it to Earth and to be able to read it. Is that the sort of your components may be involved in that communication process, or?
I don't know about a rover and Mars, but but like Leo satellites, you could communicate. There's no attenuation up in space, so you could send data at 60 gigahertz with like no attenuation from satellite to satellite, and then you down convert it to a lower frequency and send it to Earth. So yeah, we would be in some of those. Not really sure about Mars or anything like that, but yeah, we're we're more on the commercial side, but yeah, sure.
I see.
Yeah.
Okay. Very cool. Man, you're in some complex stuff. I'm gonna have to do some more reading after this and learn more about all of the language and terminology, because I know a little bit, but not enough to really dig into it.
Cool. Well, thank you
I
very
guess,
much.
yeah, thank you, Andy. Like I said, have a great rest of your day, and wishing you all the success, man.
Okay, take care.